Good afternoon, everybody. It's been very nice to see all the progress on these projects that we've been able to follow for the past couple of years online around the world. And it's neat to see all of the friends that we've made around the world through the UKHAS and various groups. For those of you who aren't introduced to me already, my name is Dan Bowen. I'm currently with the White Star Balloon Group. You may also remember me from balloon flights such as the Spirit of Knoxville, from Knoxville, Tennessee, which was a transatlantic crossing attempt. And our current group, White Star Balloon Group, is also attempting to do a transatlantic crossing with zero pressure balloons. One of the things that has always driven me personally in ballooning has been trying to explore the edges of what's possible with our meager personal funds as all of us as amateurs and our knowledge base to try and expand it and draw upon things that only professionals or governments have been able to do before and try and shoehorn them into amateur capabilities. And that leads us to today's talk that I'd like to give on the next generation of balloons after what we're using for transatlantics, which are called zero pressure balloons. These are called superpressure balloons. And without further ado, we'll go ahead and segue into my pre-recorded talk, which I recorded just in case the internet didn't cooperate, but it has much higher resolution, so we'll let that roll. Thank you, Anthony.
Well, thanks, Dan.
My name is Dan Bowen from the White Star Balloon Group in Louisville, Kentucky in the United States. Thank you for having me for the United Kingdom High Altitude Society's conference today. I'm here to talk about these balloons called superpressure. The current state of the meteorological scientific research for these has these in a category far above amateur. As you can see from some of these photographs, they're as big as football stadiums and have to withstand incredible pressures and incredible tensions to successfully operate throughout their multi-month and year lifespan, holding many tons of payloads. However, what we're going to discuss today is how amateurs can in fact try and follow along the path that scientists followed to generate the progress from no knowledge to the current state of superpressures. And we'll see that it just might be possible. As you can see, these pictures are progressing backwards through time to steadily more simple superpressure balloon designs. And the question we're to address here is, how can we do this? Superpressure balloons don't necessarily have to follow the modern paradigm. The initial research to these was of very simple designs called tetroons. These require very little material, very little seal length, and the seals are straight. The current state of amateur balloons is typical of this, of party balloons, thanks to Steve Randall for that. But the current amateur balloons don't work. As has been tried many times, I'm sure most of you have watched on the spacenear.us tracker with James Coxon and others' flights. The superpressures, while in theory should work, have just not been matching up to the theory in practice. I've done a lot of research over the past couple of months in terms of why this might be happening. And what I've found is most of the academic papers on this subject are freely available from the United States National Center for Atmospheric Research archive, one of the few scientific journal locations that seems to have all free access up until the recent year or so. The problems that scientists came across back in the 1950s and 1960s we'll go over here now. Typically, the superpressure balloons' lives would be ended by either gradual helium leaks, bursting, insufficient superpressure at night, or descent due to weather-added weight. The gradual helium leak It's fairly self-explanatory. Bursting, you've all seen with rubber balloons, and we can imagine how it works with superpressures. And the last two, though, are fairly unfamiliar to typical rubber balloon flight. While a balloon may achieve a pressure internally greater than the air around it, it has to make sure that at night, at the coldest temperature of the gas, that there is still a positive pressure inside. And the amateur superpressures today certainly show no sign of doing that. The one flight that I do recall that successfully superpressured was Soli Deo Gloria 6 in about 2007 or 2008 by Robert Rockty in the United States. Did not successfully superpressure enough to stay fully inflated at night, and it descended at sunset. Also discovered is the descent due to weather-added weight of moisture, and that is either by condensation, frost, or actual ice particle deposition from cirrus clouds or other cloud types, typically seen solely in the troposphere through most of these phenomena. Why do we get these problems? The study through these academic papers has turned up several reasons, as you can see here. The plastic envelope film that we're using is prone to generating small holes in the mylar, which is typical of the grocery store balloons. The seams and seals are not well chosen. The research shows that lap seals, fin seals, and wrinkles are primary causes for seal failure, and the grocery store balloon uses a fin seal, for example. The balloon stretch is a foreign concept to most of our superpressure musings, and it actually needs to be calculated, and it's probably one of the primary reasons why the initial flights by James Coxon and others are not superpressurizing properly and are bursting frequently. Imprecise launch preparations and calculations. Launch prep, we can obviously get that more precise very simply. Calculations, that's quite a bit more difficult to make more precise, but that's what my goal is here, to introduce you all to the concepts of how we might do that. Incorrect solar radiation absorption estimates. This directly goes to the equations of where you need to calculate the daytime superpressure and the nighttime superpressure estimates to ensure that your balloon remains pressurized day and night, to maintain altitude day and night. Right now that seems very hard to do, and looking through the academic research, they echo that it is very hard to do. The nice thing about it is, though, that we have lots of meteorological flight data to show us some good examples to make some educated guesses, and some nice data on materials research that a lot of companies, that Winzen has done in the 1980s and 90s to characterize some of the modern materials, solar absorption and radiation. And again, the weather, when you get water on the balloon, it will come down. And that primarily happens at low altitudes. We're talking below 10 kilometers, below 10 to 15 kilometers. So if we want a superpressure to stay up for a long time, it's got to be high. How can we solve these? Use better films. Heptax, Capran, or Emblem. I'm going to experiment with Heptax this winter. Capran and Emblem have been studied in these studies by Winzen. You'll see cited at the end here. I believe Heptax is very similar to Capran or Emblem, both. Sealing, use a butt seal, which means put both ends of the material together end to end and then run a thermal adhesive covered tape of the same material over the seam on both sides. That has been the best results in the spherical balloon testing. Presumably that would work with tetroons. The tetroons are designed inherently to be less complex, and you can get away with the fin seal on a tetroon for research understanding that tetroons are never going to give you a very long duration flight in terms of weeks or longer, but is a great place to start. So measure stretch in the lab with an actual balloon. Build your balloon, your superpressure balloon, and then measure the stretch when you pressurize it to your estimated superpressure with a helium apparatus in your lab. And measure the lift of that when it's pressurized and when it's not pressurized to get the actual volume change of the envelope due to stretching. And that has to be then taken into account in the math for selecting the proper payload weight and possibly redesigning your balloon to accommodate the appropriate stretch. And again, choose the altitude above the troposphere. Also, supporting the payload shows that it's not the greatest idea to support the payload from anything attached hard to the envelope. The best results have been loose loops of cable or rope over the top of the spherical envelopes that were studied, allowing them to slide freely so the balloon could expand and contract day to night without any tension from the payload. As far as tetroons, there's not any information I've seen about that, and typically tetroons are mounted at the bottom point to the payload. Adding an aluminum reflector cap that's aluminized mylar seems to be pretty much a good idea to minimize your day-night temperature swing, both to reflect some of the sun and more of preserving the infrared radiation of the helium from going out into space at night and reflecting back in the infrared radiation from the ground into the balloon at night. And of course, the purpose of today's talk, mathematics, is going to help us more than any of our guesses so far. We have done a great shot at superpressure math. Steve Randall has put together a nice spreadsheet that seems really good in theory, but when we look at using it in real flights, it has not given us the results we expected it to. So that's why we went ahead and looked at more of the past scientific research to find out what was going on. And it turns out there's a lot more going on than intuitively expected. And even in the 1950s and 60s, the academic researchers at the University Corporation for Academic Research went through the same problems. They created fairly simple maths as we did in the amateur community and found them to be not matching the real empirical data, and went through some long, complicated flight research series for 20 to 30 years before they finally arrived at what was really going on in some cases. Thankfully, all of these most of these papers that I have seen references to are freely available online. I will give full citations at the end of this presentation, and of course make this all available on the web with citations and links. Can we do this math that I have seen in these papers? Likely, but it's not the kind of math that we're going to be able to do on the launch pad, and it's going to be math that beginners and normal hobbyists are not going to want to bother with or probably be able to understand without a lot of head scratching and a decent math education already. So, what do we need to do? This is a couple of the primary maths we need to perform. The volume change rate, which comes from mid-air stretch. If this volume change rate is too high, your ascent rate coupled with that will actually cause a runaway expansion and cause the superpressure balloon to burst. We need to calculate the day-to-night pressure drop. We must leave this balloon plastic film tight at night. There should be no slackening, so we must have positive pressure at night. And to calculate that, you need to know the thermal radiation absorbed during the daytime by the sun to calculate the high temperature inside in the daytime, and some of the information about radiating infrared at night to know the low temperature at night. These things Well, they are complicated, and the academic papers are very much overlapping in their coverage of these subjects, and some are conflicting. We haven't entirely sorted out exactly which ones are going to be the final ones to try in the air, but I've put together a couple of the interesting ones just to show you. I won't cite these in particular or explain them in details, but would at least like to show you some of the information we pulled up to give you some background. I'll just let these go by with the minimum commentary. As you can tell, some very interesting content there. Went by a little fast, but these are all just screen captures out of the academic papers we'll link to later. Most of these tables were out of the 1990s report on superpressure technology by Winzen, actually in the maybe late 80s, early 90s. This is the question. In all of this, and I think they can. I think we can. It's just going to take a little bit more work. And to do that, I've partnered with a math graduate student here at the University of Louisville, Eileen Bonkowski, who has actually gotten quite involved in this research and has proposed to write a very comprehensive tool to help through all of the possible calculations that we're running into here that need to be determined. This app will have several small sub-calculators embedded in it to help you to measure the stretch and volume while you're on your bench with the helium balloons, several other small sub-steps that are important in doing the day to night temperature calculations and things like that. And help you with some likely suggestions for what to put into these input fields when you don't have enough information to put in real numbers, like solar radiation and whatnot. We're going to make sure that this tool is easy to just hit start on with the minimum of knowledge. For example, I want to go to this altitude with this payload. Tell me how to build a tetroon. And it will do so with the best guess that it can based on what you've suggested. And we're going to make this automatically select or let you choose units and have it automatically convert for any typical set of units, be it SI or imperial or others that are more engineering oriented. Eileen is going to write this in MATLAB at this point. This is just a very early sketch of this plan for this program. We're still in the research stage, but looks like MATLAB we can export executables to 3 different platforms, and we're going to target a release for January 2012. If you would like to get involved with this, for example, if you have experience in exporting MATLAB to binaries and things like that, making whatever more on the math side, and you'd like to be involved in the planning of this, the user interface, whatever, go ahead and email Eileen directly about this project. She's spearheading this, and I'm helping her understand the superpressures side of it, and she is the programming and math genius behind this plan here. As I said before, this is all going to be sighted, and here you go. Again, I'll provide these online at whitestarballoon.com/superpressure. That's whitestarballoon.com/superpressure. If you have trouble copying down from this video. These are fantastic papers to read, by the way. Bedtime reading, I highly recommend for balloonists. Just really interesting experiments, commentary, weather information, and mechanical and electrical information about how they did these balloons back in the old days. And again, my name is Dan Bowen. I'm with the White Star Balloon team, and we've been doing a transatlantic balloon project with zero pressure balloons, not super pressure, and we do hope to cross the Atlantic sometime this winter. So for any questions, you can direct them to me. I hope to be available on an audio Skype link here momentarily after this presentation. And if you have any questions later on, please email me at steamfire@gmail.com there on the screen. All right, well, I hope you all enjoyed that, and I would love to entertain any questions about this interesting next step. And I do want to reiterate that this information that I presented here was, as far as I could, not conjecture on my part. It was directly taken from the scientific literature, published scientific literature. So it has actual experiments to back up the conclusions that they've come to, and that puts a little bit more stock in them than not doing experiments, just coming up with it on our own. And I would definitely like to welcome collaboration on the tool that we're going to work on, and we're going to work with Steve Randall as well with his spreadsheet to see how that can be improved and possibly work together on the tool with him. So any questions from there? And Anthony, if you could, let's see, if you could relay them to me on.
Yeah, sure. The speaker's actually quite good. Ed's putting his hand up, so I'll just try him. I'll let him shout loud.
Yeah, I can hear.
I was wondering if you had any thoughts on approachable manufacturing techniques for these balloons for animals.
Yes, absolutely. That is one of the subjects covered by these papers in light detail. They don't go to great lengths, but some of the early papers, you'll notice the 1960 paper in particular is very useful for that topic. If you use a film that consists of multiple layers of mylar with polyethylene on the back, it gives you a heat sealable film. And the tetroons built in the 1960 paper and several others were made with a straight long seal for all the edges. And that's a seal that we can do very easily with a commercial bar sealer for bags, for commercial bag production. You can get them about a half a meter to a meter long sometimes for probably about 200 pounds. I know that's expensive, but as a group, we can, shell out for that sort of a thing. And tetroons are only good for short duration flights, as in a day to a couple days. Beyond that, you'll probably have to switch to spherical, just judging on what the scientists migrated towards for long flights. And spherical ones are obviously going to be immensely more difficult than the tetroons. So that's a ways down the road. But even still, we've gotten the techniques that they refined through years of trial and error down to the basic idea of you have to cut the balloon gores and leave circles at the top and the bottom. And to attach all the seals, you need to do a butt seal, like I mentioned there, and you need to put an actual thermal adhesive, not a contact adhesive, and not a solvent-based adhesive, but basically hot glue spread on the same film and used as a tape on the outside and the inside of the seams. And that seam technique is what enabled the Ghost series of balloons launched by Vincent Lally in 1967 to circumnavigate the world over 30 times for one balloon and stay in the air for 700 plus days for one 2-meter diameter balloon. So even if we do mediocre seals on that type of balloon, it should be impressive results. Any more questions?
Yeah, 1 second, Lawrence. Do you want to just? I'm not going to turn around here. I'll just direct the microphone to you.
Hi. Yeah, do you actually think it's possible to get a float with a tetroon?
Yes, absolutely. A lot of the early papers deal exclusively with tetroons, and they deal with the ones that were successful and unsuccessful, but they still today are used as a standard meteorological tool for evaluating constant level wind patterns. They're very quiet about the production of them. I believe only Aerostar is maybe the only source for those, and I've never come across them on the open market, but there's still references to those being used for floats. They just never seem to have gotten used for long duration ones. And one of the clues I've seen in the papers was that the corners of the tetroon end up getting stressed more than the rest of the tetroon, and that's usually what ends up failing.
Yeah, that was my understanding of the problem with tetroons. But yeah, it's interesting if there isn't such a considerable stress build-up.
Yeah,
that it does actually work.
Yeah, from the numbers that I've seen in these papers, the difference in weight and helium fill is the margins are very, very narrow between having a successful float and enough pressure in the daytime and also enough pressure at night. Basically, there's very little margin between that successful condition and a burst. So it's going to be something where we have to be very precise with our calculations, or randomly lucky to get it. It's not a wide target we can aim for when we're trying these flights, and I'm afraid that's why a lot of the foil ones have had so much trouble, is because it's we have to test more characteristics such as stretch in those foil balloons, and they might work for some durations afloat if we can characterize their behavior a little bit more precisely.
Do you have any figures on how much worse the stress buildup is with a tetroon than with a complete spherical balloon?
Not from memory, but I believe some of those papers do discuss that. And I can, I'll write that down and get back to you.
Apparently Bill is mentioning that there have been successful superpressure flights using a mass flow meter to precisely measure the helium.
Ah, that sounds like a great idea, yeah. Knowing how much helium is in there is really critical. The technique used by the early researchers was a very simple one that you're familiar with, which is simply measuring the lift of the balloon with very precise scales.
Okay, thanks.
Any other questions?
No, that's good. Well, thanks so much for that, Dan. Much appreciated.
Yes, thank you all for having us there. It's great to get to see you guys.